Hi everyone, welcome to the classes on engineering mechanics, and today's our topic is mechanical vibration. I think most of us is heard about the term vibration. If any body is moving to and fro, is continuous to and fro motion, and with respect to an equilibrium point, then it is called the mode is under vibration. So we have many examples in our day-to-day life, like our pendulum of a clock, or our while traveling in our bike, we will feel vibration. All these are comes into the mechanical vibration. Okay. A mechanical vibration is defined as a measurement of a periodic process of oscillation with respect to an equilibrium point. Okay. And next we will go to the classification of vibration. First, the classification is classed the free vibration and forced vibration. Free vibration is again classified to three times. First one is longitudinal vibration, second one is transverse vibration, and the third one is a torsional vibration. You can see three figures here. All these are a disc is attached to a flexible rod. In the first figure, the disc is given a particularly downward movement. Then it will come to its equilibrium position by an elastic force, and it cannot stop at the equilibrium position. It will move some point upward, and it will continue its motion for some time. After that, it will come to its equilibrium position. This will cause the vibration of the body. In second figure, again the disc is given a displacement in towards left or right direction, and again the disc will try to come to its equilibrium position, and it cannot stop its equilibrium position due to the moment of inertia, and it will continue its motion for some time, and it will come back to the equilibrium position. That is a transverse vibration. In the third one, the disc is given an angular displacement. The disc is rotated with respect to a center, and the point A will reach the point C, and then it's released. Then the point A will try to come back to its equilibrium position. Again, the moment of inertia will come to act, and it will continue its oscillation for some time, and it will come to rest after some time. And this is called a torsional vibration. In next classification, we will be dealing with the forced vibration. Free vibration we have discussed here, and the pendulum of a clock is also a very good example of a free vibration. Okay. Okay. Not pendulum of a clock, it's a simple pendulum. For a pendulum of a clock, it will not stop its vibration. If any body is given an excitement, if there is no resistance offered to the body, it will continue its vibration. Otherwise, it will stop the vibration. Normally, we are giving oscillation to a simple pendulum in our normal atmospheric condition. So, air is there, so air will offer resistance to the motion. So, air will offer resistance to motion, so the vibration will be diminished. For a forced vibration, suppose the pendulum is inside the clock. The pendulum is operated with the help of a battery. For every oscillation, the battery is giving a small amount of power to keep the pendulum oscillating. That is called a forced vibration. So, pendulum of a clock is an example of a forced vibration. At a periodic interval, it is excited by an external force. That is called a forced vibration. If the pendulum, normally we will be doing the experiment in our physics. If we are giving an oscillation to a pendulum, it will continue its oscillation for some time, and after some time it will stop the oscillation. And the reason is the resistance offered by the air. Even in the clock's pendulum there is a resistance by air, but the oscillation is continued with the help of an external force called a battery force. Another example of a forced vibration is the engine of an automobile. So normally we will be dealing with a four-stroke engine. In the four-stroke we will have only one power stroke. Due to that one power stroke we will be getting power, and it will create an oscillation, and this will be repeated in every cycle. So the engine will feel a vibration by an external force. That is why it's called a forced vibration. The next classification is a damped and undamped vibration. But damped means, suppose the vibration is reduced with the help of some medium. Normally we will be giving oscillation to a simple pendulum. The pendulum oscillation is diminished or reduced because it is kept in the atmospheric air. And suppose we are keeping the pendulum inside the water. Again it will oscillate, but the oscillation will stop more faster compared to the air. Similarly, the medium which will offer resistance or which will be used for reducing the vibration, that is called a damped vibration. Suppose in any medium is used for reducing the vibration, that is called a damped vibration. Then suppose no medium is used for reducing the vibration, that is called undamped vibration. Okay. As the next classification is deterministic and random vibration, and this is clearly explained with the help of a graph. You can see the first graph. It's a example of how the force is acting on an element with respect to time. Suppose in the first graph, the force is acting at a regular interval. Initially the force is at the maximum point and it is reduced, then it is again reaching a maximum point and it's reduced. So the force is acting at a regular interval, so the vibration will follow a regular pattern. That is called a deterministic or periodic excitation, periodic vibration. In the second figure, the force don't have a regular pattern. Sometimes it will have the maximum value, sometimes it will have the minimum value, sometimes it will remain in the positive region, sometimes it will remain in the negative region. So it is called a random vibration. We cannot predict the body or nature of the vibration. That is called a random vibration. So this is all about the classification of vibration. Okay. So we have discussed about free vibration and a forced vibration. Free vibration also is called natural vibration. We got three types of free vibration: longitudinal, transverse, and torsional vibration. Next will comes the forced vibration, then the damped and undamped vibration, then the deterministic and random vibration. Okay. Next one is the period of vibration. Period of vibration, suppose we will have a simple pendulum, it will start oscillating and it reach the maximum point, it will reach the next maximum point, it will reach the original position. That is called the period of vibration. The time taken for the element to complete one cycle, that is called the period of vibration. Okay. The time interval after which one motion is repeated itself, the period of vibration is, or the time period is usually expressed in second. Okay, it is the time only, it will be expressed in second. The motion completed in one time period is called a cycle. Okay. Next one is the frequency. It is the inverse of time period. Suppose 50 is the time taken for one cycle and 1 by 50 is the frequency. Okay. Suppose, so number of cycles per unit time is called the frequency. Frequency or free vibration is called the natural frequency. In SI unit of frequency is called hertz. We already heard that normally in our house the electricity coming with a frequency of 50 hertz. That means the AC current, it will be a sine wave, it will be oscillating 50 times in a second. If the frequency is 50 hertz, the time period will be 1 by 50. That means in 1 second the AC current wave will be oscillating, completing 50 cycle. That is called the that is mean by our current is 50 hertz. Okay, 1 hertz equal to 1 cycles per second. Okay, time period is denoted by TP and frequency is denoted by F, which is equal to 1 by TP. The next thing is the stiffness of a spring. In our next topic we will be dealing with the springs. Normally we will be dealing with we have familiar with the spring in the pen, also the spring in the shock absorber of a two-wheeler. Okay, it's a very common example. Suppose we are applying force on the spring in our pen with our two finger. We can give a displacement, we can compress the spring from its original position to a new position. Suppose we are applying the same force on our spring of a two-wheeler automobile, it will not compress. So it will have a greater resistance to the force compared to the spring in our pen. So that is called the simple explanation of a stiffness. When a spring is compressed, the spring opposes the applied force which compresses the spring. The opposing force is proportional to the displacement of the spring, and that is spring force is proportional to displacement of the spring. Okay, so F is proportional to S. This proportionality is replaced by a constant that is called the spring stiffness. Okay, F is equal to K into X. or K is equal to Fs spring force divided by displacement. Force, the unit of force equal to Newton and displacement unit is meter. The stiffness unit will be Newton meter. Okay. Next one is the natural frequency of longitudinal vibrations. This is a derivation which will be have normally they will ask for the university examination, in which we will be dealing with a spring mass system. Okay. So in this figure you can see initially first figure you can see a spring, and the second figure we have attached a mass m to the spring. While attaching the mass, the spring is elongated by a distance delta. Okay. So the force acting on the spring is equal to the weight of the mass we have attached and the deflection or the spring force equal to K into delta. So that now the system is in equilibrium. The next thing, we are giving an external excitement of displacement x to the spring. So it will cause an extra displacement x plus delta, and due to the displacement the spring will experience an acceleration. Okay, that is the concept. So here is our first equation. Was in the initial case mg is equal to k delta, and we are giving extra displacement x plus delta. This is the total force, that is equal to mass into acceleration. F is equal to ma. Okay. Now we are equating the terms, expanding the bracket, mg minus kx minus k delta equal to m into acceleration can be expressed as second derivative of displacement, d square x by dc square, and k delta is equal to mg, so it got cancelled. Our equation will become minus kx equal to m d square x by dt square, and we are writing it in terms of an equation, d square x by dt square k by m into x equal to 0. Okay. So we are comparing the given equation d square s by dt square plus k by mx equal to 0 with the equation of a simple harmonic motion. For simple harmonic motion, d square x by dt square is equal to minus omega square x. So we are comparing this equation, we can write k by m is equal to omega square, or omega is equal to root k by m. So it is called the natural frequency of vibration. Since we are only given the external force, then it is keep on vibrating. We are not giving additional force for each cycle of vibration, though, so it is called a natural vibration. So omega n is called the frequency of natural vibration, omega n, and we can write omega is equal to 2 pi f. So f is equal to omega by 2 pi. By using this equation, we can write natural frequency of vibration 1 by 2 pi root k by m. Okay. The next thing we will be dealing with the degrees of freedom. In the first figure, a mass is attached to a spring. When we are giving excitation, the mass will be oscillating in the up and down direction. So the motion of the wheel happen in only one direction. So it will have only 1 degree of freedom. And the second thing also, a mass is attached with the help of a string, and we are giving an angular displacement, then leaving, it will oscillate in this direction. Again, this will have only single degree of freedom. Okay. And the third thing also, again a mass is attached to a spring, with the help of a pulley. The motion of the spring will depend on the mass only. This is all example of a single degree of freedom. In the second figure, here you can see mass m1 and mass m2. The motion of the m2 will depend on the spring x1 and x2. So m2 will have a 2 degree of freedom, but the m1 will depend only the spring x1, so m1 will have a single degree of freedom. Second figure, again the similar example of our simple pendulum, but the string is replaced by a spring. So the movement of the body m will depend on the angle, also the elongation of the spring. So again the mass will have a 2 degree of freedom. So these two will have a example of 2 degrees of freedom. That's all about the degrees of freedom. Degrees of freedom have a definition. Degrees of freedom is have a definition. The number of degrees of freedom of a physical system is the number of independent spatial coordinates required to define the configuration of the system. So in the first three figures we require only one. For the first figure we require the moment of the spring, second figure we require the theta, and the third figure we require the moment of the spring. These three required for the defining the position of the mass. In the second, fifth and sixth figure, for the mass m2 we require the moment of the spring x1 and x2 for defining the position, and for the fifth figure again the mass position of the mass is defined by the angle theta and the spring. So it will have a 2 degrees of freedom. Normally a rigid body in space have 6 degrees of freedom with the coordinates x, y, z, and for the rotation in all these three coordinates. Okay. So next topic we will be dealing with the spring mass model. So normally we have to do problem with more than one spring. Sometimes the springs are connected in series, sometimes the springs are connected in parallel. So we have to analyze both these cases and find the equivalent stiffness of the spring. Okay. Here is the first case. The springs are connected in series. With both the three springs have the stiffness K1, K2 and K3, and each spring will produce a deflection delta 1, delta 2 and delta 3. The total deflection is equal to delta, which is shared by delta 1, delta 2 and delta 3. So we will write the equation delta equivalent is equal to delta 1, delta 2 plus delta 3, and the total mass acting downward is equal to mg, that is equal to k delta. So delta can be written as mg divided by k, or delta 1 can be written as mg by k1, delta 2 can be written as mg by k2, delta 3 can be written as mg by k3. So total delta is equal to mg by ke. So we can equate this term and we will be cancelling all mg's, or we can write the equation for the equivalent stiffness 1 by ke is equal to 1 by k1 plus 1 by k2 plus 1 by k3. So we have to study this equation only. Sometimes they will ask for the derivation. So then you can use these steps. So this is the equation for the spring connected in series. The second thing we will be dealing with the spring connected in parallel. Again the three spring K1, K2, K3 are connected in parallel, which will produce a deflection delta. We will be replacing with another spring that will have the same stiffness K equivalent. Again mg is equal to, we will have the delta K1 delta plus K2 delta plus K3 delta. We will be taking the delta outside, K1 plus K2 plus K3. mg is replaced by K equivalent into delta. So K equivalent equal to K1 plus K2 plus K3. That is the equation for equivalent stiffness of a springs connected in parallel. So if the springs are connected in series, 1 by K1 plus 1 by K2 plus 1 by K3. If the springs are connected in parallel, 1 by K1 plus K2 plus K3. It is almost equal to the how we will be calculating the capacitance normally in a electrical circuit. Okay. So we will have some problems in connection with the spring mass model. We will be discussing in that our next class. Thank you.